What if, all of a sudden, the laws that keep everything in place were to fail? You drop the cup, and it doesn't fall. The sound of traffic arrives late. The shadows stand still for a second. It's not a miracle. It's reality losing its instruction manual. For forces dictate what can and cannot happen: gravity, electromagnetism, the weak force, and the strong force, and a handful of constants that we swear are immutable, until they aren't. If gravity fluctuates, seas rise for no reason, satellites lose their way, buildings breathe as if they were creatures. If electromagnetism stumbles, the light flickers, chemistry fails, and our neurons begin to communicate in noise. If the strong force varies, stars fade or explode prematurely. The core of the atom forgets how to remain whole. If the weak force becomes unregulated, decay becomes a gamble. Nuclear clocks go haywire, measurements lose their way. What if the speed of light ceases to be a limit? Messages arrive before they are sent. Cause meets effect on the wrong side of time. The past loses its obligation to come first. The stranger who once lived confined to the laboratory escapes. Doors open late. Shadows arrive early. You swear you experienced something yesterday, but it was tomorrow. Memories begin to contradict the facts, and no one can prove who is right. It wouldn't just be chaos. It would be a geography of broken rules, neighborhoods with different gravity, cities where light travels slower, invisible borders that clocks don't cross. Compasses spin silently, and the ground weighs more than it should. Technology falters first. GPS becomes guesswork. Circuits contradict each other. The internet chokes on packets that leave but never arrive. Then comes biology. Our internal rhythms become misaligned. Sleep loses its rhythm. The heart tries to keep up with a time that is no longer reliable. And us? We try to impose meaning on what doesn't negotiate with meaning. We look for patterns in the noise. We invent local laws. We recite formulas like mantras, hoping that the universe will still respect them. But if the rules are cracking, what is still real? What does before and after mean when time itself hesitates? Who are we when the next rule may not exist? If the laws of physics cease to function, it wouldn't be the immediate end of everything. It would be worse, a world that seems familiar until it isn't anymore. And in that narrow space between what we know and what has ceased to make sense, the haunting question arises: how to live when reality doesn't obey? First, the lights begin to fade, not all at once, but like an audience that silently rises and exits through the back door of the cosmos. Stars that have burned for billions of years begin to flicker as if something outside of reality. We're closing the curtains. It's not the end of energy. It's the end of the rule that allowed energy to transform into light. Nuclei that once fused hydrogen now hesitate. Fusion doesn't stop. It's the permissibility for it to happen that crumbles. And the sky, which has always been a map and a memory, becomes a panel of blackouts. Meanwhile, space reveals seams. Distant points that should never touch emerge side by side, like glued pages of a poorly bound book. Straight lines curve where there is no mass. Distances change their meaning midway. And what was continuous displays thin cracks, tears that whisper a no to our equations. You take a step, it measures too. A spaceship crosses a known void and returns in a different geometry. The map isn't wrong. It's the board that's broken. And then time fails, not like a clock without batteries, but like a law tired of commanding. Before and after cease to be a cue and become a crowd. There are moments that repeat themselves with slight differences. Like echoes that have learned to improvise. There are mornings that arrive too early, and nights that refuse to end. The cause goes out for a smoke, and the effect happens anyway. Memories shift. You clearly remember something that hasn't happened yet. And when it does, it is not identical to your memory. It acts as if the future heard your story and decided to tell it differently. With the stars fading, orientation disappears. Without lighthouses, galaxies lose their sense of direction, and we lose our sense of scale. With space tearing apart, reliable routes crumble. No old road can cross a new rift. With time failing, plans become superstition. Making a date is an act of faith, and promising tomorrow is like throwing a coin into a bottomless pit. You look at the sky and don't find the sky, you find a sketch. You check the clock and it gives you a guess. You reach out and the place where your hand should be is delayed by a fraction that no one can measure. It's not the cinematic apocalypse. It's more intimate and more disturbing. It's the fabric that clothed us loosening its stitches, one by one, stars fading, space tearing apart, time failing. If reality was a sentence, someone removed the punctuation, and now everyone reads it as they can. Who are we when even now needs a caption? The universe may be collapsing right now, not like a final bang, but like a weariness that arrives first at the edges, a subtle delay in the light of a distant star, a tiny deviation in the path of a satellite, a perfect clock that, for an instant, swears it has heard time breathe. We call it noise. Perhaps it is a warning. Think of a vacuum, what we believe to be nothing. What if that nothing is unstable, like thin ice? A bubble of a more true state could silently emerge, expand at the speed of light, and rewrite all the laws in its path. There would be no siren, no shadow coming, just a sudden rule change on the other side of your next blink. Or perhaps it's dark energy, that invisible accounting that pushes galaxies apart, changing moods. If it's becoming more aggressive, space stretches too far, the bonds give way, and the universe begins to break apart from within, first separating what is fragile, then what seemed unbreakable. It's not cinematic apocalypse, it's a slow loss of cohesion, a crack you only notice when water has already seeped in. There's yet a third whisper, microscopic changes in the constants we swear are immutable. If the how much allowed for light, matter, and time fluctuates even slightly, atoms reassess promises, reactions hesitate, and the cosmos's calendar slips, the signs would be subtle, scattered across 1,000 phenomena that don't add up. The enigma doesn't reside in one place, it resides in the pattern that no one wants to see. Right now doesn't have to be a spectacle, it can be a process. Collapse doesn't announce itself with a flash. It reveals itself as an accumulation of small impossibilities that we begin to accept. Each night, one less point in the sky. Each decade, one more adjustment to our equations. Each life, the feeling that the world is slightly out of balance and that this slightly has grown when we weren't looking. If the universe is collapsing now, our perception is the first line of defense. To notice is to resist the comfort of easy explanations. To ask questions is the antidote to sleeping while the ceiling descends. Because the end of the universe, if it comes, will not be just a physical event. It will be a test of attention. And perhaps the right question is not when does it end, but what do we do with the time we have left while the sky learns to fall? Now tell me something. Which city in the world are you watching this video from? Leave a like. Share with someone who loves the mysteries of the universe. We trust the laws of physics, but what if they're wrong? Wrong not like a spelling mistake, wrong like a map that worked well in one city and starts to fail when you cross the bridge. We call law what has been repeated, what we have measured 1,000 times, and the result is the same. But what if these laws are just local agreements with reality? Agreements that are valid here, under this pressure, at this temperature, on this scale, and that unravel at the edges of what is possible. Think about gravity. It explains apples falling and planets spinning until we look at entire galaxies and the math doesn't add up. To keep stars in orbit, we had to admit something we don't see, dark matter. It works, but it's a reminder. Maybe we don't understand the rule, just the way the rule appears to work from a distance. Now try combining the very large with the very small. Relativity describes the fabric of space-time. Quantum mechanics describes the granularity of reality. Separately, they shine. Together, they creak. Like two perfect languages that, when mixed, produce noise. If the basis of the universe is a conversation, why don't these two voices understand each other? And what about constants? We call them constants because, well, we need them to be. The charge of the electron, the speed of light, the intensity of the forces. What if any of them drifts slightly with time? A tiny deviation, invisible to the naked eye, capable of changing the fate of stars. The chemistry of life, the clock of the cosmos. What if the entire universe is whispering almost the same, while we write the same? The arrow of time points forward because entropy increases. That's how we know what is past and what is future. But what if, under certain conditions, that arrow falters? What if parts of the world remember another direction? I'm not saying we'll see glasses unbreak, but that the notion of irreversibility may be statistical, not absolute, and statistics sometimes fail. What if the conservation we venerate of energy, momentum, charge is a symmetry that holds true while the stage is flat, but trembles when the stage itself changes? On cosmic scales, with space expanding, even our way of counting energy becomes nebulous. What else depends on the stage without us realizing it? Perhaps the mistake lies in our impulse to transform models into truth. Models are like lanterns. They illuminate a section and leave shadows around it. We walk in the light and conclude that the world is only what we see until we stumble upon what the lantern cannot reach. If the laws are wrong, it won't be because nothing makes sense. It will be because another layer of meaning demands another language. The universe may be saying, what you call law is an elegant approximation of my behavior under certain conditions. Change the conditions, I change the contract. So what if they're wrong? It means that reality is bigger than our formulas, that science hasn't failed, it has advanced to the limit of its current version and now calls for an update, and that the most honest question isn't what is the ultimate law, but how far does this law explain and what begins after it? We trust the laws of physics because they brought us this far, but we keep moving forward because, from time to time, we have the courage to ask, what if? Three phenomena haunt our understanding like shadows that the lantern of science has not yet reached. Black holes. These are regions where space and time bend so much that they cease to be roads and become a pit. At the event horizon, it's not the light that fails, it's the very notion of an exit that disappears. Inside, mathematics points to a singularity, a point where the equations give up. Outside, we see disks of matter spinning at absurd speeds, jets that traverse galaxies, echoes of gravitational waves like the heartbeats of invisible titans. But the question that pierces everything is simple and impossible. Does the information die there? If it dies, we break quantum mechanics. If it doesn't die, where does it hide? The universe keeps the secret with the calm of someone who is all the time in the world. Dark matter. The sky offers us an elegant trick. Galaxies spin too fast for the mass we can count. According to our physics, many of them should have disintegrated, but they remain whole, as if an invisible skeleton held them up. The skeleton doesn't shine, doesn't emit, doesn't absorb light. We know it's there because it pulls. Rotation curves, gravitational lensing, cluster collisions, everywhere, the same silent signature. We give it a name, dark matter, like someone christening a ghost, in the hope of making it solid. But what is it? Particles too shy for our detectors. A flaw in our understanding of gravity? The universe smiles and doesn't answer. Accelerated expansion. We thought that the cosmos, after the Big Bang, would be slowing down. Gravity pulls, breaks, joins. Instead, distances are growing ever faster, as if the fabric of space were under the action of a force opposite to gravity, a vacuum pressure that insists on forcing its way through. We call it dark energy, another label on a bottle we can't open. If this pressure increases, everything will separate. Galaxies, stars, atoms, us. If it decreases, perhaps the universe will recede. If it oscillates, we will be passengers in a cosmic elevator that doesn't announce the next floor. Together, these three enigmas seem to say the same thing in different dialects. Our laws work up to a point. After that, they falter. Black holes test the boundary between relativity and quantum mechanics. Dark matter requires a component we don't see or a gravity we don't yet understand. Accelerated expansion points to an energy, accounting that may be incomplete. And between what we know and what is yet unnamed, there's a territory of silence. Is there that curiosity turns into courage? Because, in the end, the universe is not wrong. It is bigger than our explanations, and that is precisely why we cannot stop looking. Do we truly understand the universe? Or have we only tamed some of its tricks? We measure, calculate, predict eclipses down to the second, land probes on worlds we've never seen up close. It works, but working is not the same as understanding. Models are maps, useful, precise, and partial. The territory is something else entirely. How many times do we fine-tune our instruments to see exactly what the model expects? How many anomalies become noise before becoming discoveries? The history of science is a sequence of this. Doesn't make sense, yet, until it does. And when it does, we realize that the new meaning didn't cancel out the old one, it only limited it. Perhaps the question isn't does the universe make sense, but on what scale does it make sense? On a human scale, cause and effect seem firm. In the quantum world, they flicker. In the vicinity of a black hole, space-time bends the rule serenely. So, when we say we understand, we're saying here, under these conditions. There's also the observer's filter. We see with biological eyes. We measure with human machines. We interpret with human language. We look for patterns because survival depended on it. But the cosmos is not obligated to be pedagogical. It can be coherent without being intuitive. What if our best physics is an elegant approximation of something we don't yet know how to name? What if dark matter and dark energy are just provisional labels stuck on doors we will one day open? What if today's impossible is just improbable with too much data to fit into our heads right now? Perhaps understanding the universe requires two rare virtues: the discipline to test what we believe and the humility to change our beliefs when the data demands it. Understanding, in the end, is not about possessing the truth, it's about updating it. So, do we really understand the universe? We understand enough to keep asking better questions. And for now, this is our beacon in the dark. When laws fail, Edmond Halley, London, winter of 1682. A man leans his face over the telescope and notes in the dark, Edmond Halley. For almost everyone, comets were capricious omens. For Halley, they were clues. He compares old trajectories 1531, 1607, 1682 and sees the same orbital signature, like three fingerprints left in different centuries. Where common sense saw chaos, he sees law. Years later, armed with the ideas, he helped publish. Halley himself financed the printing of Newton's Principia. He did the unthinkable. He wagered his own name on a prediction. This comet will return around 1758. Halley died before that date. The comet returned, and the universe responded. Gravity works only as far as courage allows. But Halley was not just the man of the comet's return. In 1718, comparing old star catalogs with modern measurements, he realized something that shattered a millennia-old certainty. The fixed stars are not fixed. Sirius, Arcturus, Aldebaran all slowly changing position. The firmament, which we swore was motionless, moves. There, it was not nature that failed. It was our provisional law that showed its limit. He also draws the first maps of magnetic declination lines, invisible curves, that cause compasses to disagree. With perfect north, an unsettling reminder, some laws are, in fact, territorial rules. They apply here, they fail there. Reality has accents. Halley teaches us the choreography of the unknown. When the law creaks, it's not time to deny the noise, it's time to follow it. The returning comet, the drifting star, the stubborn compass. Each anomaly is a note from the cosmos saying, the next page is this way. Today, faced with black holes, dark matter, and accelerated expansion, the lesson remains. It's not physics has failed, it's this version of the law has run out of steam. When laws fail, it's not the end, it's a doorway. Halley crossed one of them and left the light on the other side. It's up to us to continue. Uncontrolled cosmological constant. Edmond Halley. Imagine Halley today, not on the London docks gazing at a comet, but facing the void, that nothingness that pushes everything. In place of the icy tail, it would follow a Greek letter, lambda lambda, the cosmological constant, a silent background pressure that makes space stretch. Einstein included it in the equations to keep the universe static. Later he called it an error. Decades later, the sky responded. Galaxies are moving away from each other faster and faster. The error seemed like the missing piece. If Halley taught us anything, it was this: when reality creaks, follow the noise. But what if lambda is not constant? What if it oscillates, grows, or changes phase? An uncontrolled cosmological constant is the universe with its foot on the accelerator without a reliable speedometer. If increases over time, vacuum energy becoming more negative in terms of pressure, galaxies separate, clusters break apart, and in an extreme scenario of ghost energy, even atoms could be torn apart, the so-called big tear. If decreases or changes sign, the expansion slows down, gravity resumes control, and the cosmos may tend toward a contraction, a grand collapse on an unimaginable scale. If jumps to a lower value, because the vacuum is metastable, a bubble of new laws can be born at one point and expand at the speed of light, rewriting physics along the way. Without warning, without a flash, what clues would Halley follow? The same things that already whisper in the data. Supernovae fainter than expected for their distance, the dance of the cosmic microwave background. The way structures grow over time. He would compare catalogs as he did in 1718 with the fixed stars and discover, again, that the fixed moves. He would look for subtle variations in the state parameter W, that pressure-energy ratio of the vacuum that decides the fate of the cosmos, hunting for trends like someone tracking the return of a comet. Halley wouldn't call it an apocalypse. I would call it a testable hypothesis. I would wager predictions. If lambda is rising, such a gravitational lensing pattern will appear. Such a galaxy growth curve will deviate. Such a cosmic clock will arrive early. And I would leave the wager written down, as he wrote about the comet ready to be disproven or confirmed by the heavens. A runaway. Cosmological Constant isn't a disaster movie. It's the uncomfortable question: are our final laws truly final, or just the best local version? If Halley were here, he would repeat the method that immortalized him. Name the anomaly. Follow it fearlessly. Demand a verifiable answer from the universe. While L breathes, gravity holds its breath, and we, with Halley on our shoulder, learn to listen when the void speaks. Dark matter and dark energy. Invisible controllers. Edmond Halley. If Halley were alive today, he wouldn't just focus on a comet's tail. He would point his catalogs at two empires that govern the cosmos without ever appearing. Dark matter and dark energy. One protects, the other repels. Together, they choreograph almost everything and leave us in the dark. Dark matter, the hidden skeleton. Galaxies spin too fast for the mass we see. According to our textbook, they should disintegrate, but they don't. Something invisible pulls them. Halley, who one day realized that fixed stars move, would recognize the pattern when the sky insists on impossible behavior. The law we are using is insufficient. He would do what he always did: compare catalogs, rotation curves, gravitational lensing maps, cluster collisions. He would superimpose centuries of data as he superimposed stellar positions, and from the noise, extract constancy. There's a skeleton that doesn't shine, but leaves marks in the path of light. Where the light bends, its presence reveals. I was here. Dark energy, a push from nothing. We expected the universe to slow down, held back by gravity. Instead, distances are growing ever faster. It's as if the void has pressure. Halley wouldn't be intimidated by the name dark energy is just a label. He would hunt for cosmic clocks, supernovas that fade with predictable brightness, fossil ripples in the microwave background, the rate at which structures grow. If the push accelerates, certain signals advance. If it slows down, they lag. He would bet on numbers, as he bet on the comet's return. At such and such a time, the expansion will have this rate. If it doesn't, my hypothesis is wrong. Methodical courage. Two invisible hands, one visible method. Dark matter binds the cosmic web. Dark energy stretches the fabric between the knots. One organizes, the other disorganizes, and the universe is the blueprint left over from the conflict. Halley would map both with the same stubbornness with which he mapped the variation of Earth's magnetism. Lines of force that no one saw, but which guided compasses. Now, the compasses are distorted beams of light, galaxies deformed in the distance, atomic clocks out of sync by a hair's breadth, weak signals, strong pattern. And what about skepticism? It would be part of the script. Halley would ask if we aren't confusing new matter with new gravity. I would test the two ideas side by side and let the heavens decide. If it's matter, silent detectors will one day pick up the signal. If it's gravity, the mathematics will change its focus on large scales. In any case, the lesson is the same. When we don't see, we measure better. In the end, Halley would remind us that invisible is not synonymous with mystical. Invisible is simply what still requires another instrument. He would leave us with a map of bets, weak lens patterns at such distances, growth of structures with such inclination, small differences in the pace of expansion over time. If the map matches, we will not have seen the controllers, but we will have felt their hands on the steering wheel. Dark matter, dark energy, invisible controllers. Halley would light the lantern where ours goes out. Name the anomaly, follow it fearlessly. Demand from the universe an answer that may be right or wrong in writing. That's how you draw the invisible until it surrenders and takes shape. If Edmond Halley were alive today, he would trade Comet catalogs for space-time curvature maps and quantum probability tables. He would quickly understand the drama relativity describes a smooth, continuous universe where mass and energy curve the stage. Quantum mechanics describes a granular, uncertain universe where measuring is already interfering with the play. Separately, they are symphonies. Together, the pentagram catches fire. In the most extreme corners, singularities of black holes and the first moments after the Big Bang, the two theories need to converse. That's where the mathematics explodes into infinities. The equations of gravity refuse to renormalize as quantum forces do. Quantum operators want local rules on a stage that relativity says changes with the drama itself. It's like trying to measure an ocean wave with a ruler that deforms with each break. Halley would recognize the scent of that boundary. In 1718, when he noticed that the fixed stars were not fixed, he did the difficult, obvious thing. He compared catalogs over time. Here, he would compare catalogs of paradoxes. Does information disappear into a black hole or survive, encoded, on the horizon? Is time a geometric fabric or an emergent effect of quantum correlations? Is space-time continuous or a discrete network that large-scale disguises? On one hand, relativity demands rigorous causality and smooth trajectories. On the other, quantum mechanics offers apparent non-locality and superpositions that mock our intuition. When we try to put the two on the same table, scenarios arise where space-time, at Planck scales, becomes boiling foam. Calculus demands 0 times infinity and doesn't know what answer to give. Mathematical chaos here is not a mess, it's the universe saying my language changes in this frequency range. What would Halley do? The usual, verifiable bets. He would write notes to the future, as he did with the comet, clocks in extreme gravity. If gravity is quantum, certain atomic clocks near intense fields will show residual fluctuations beyond relativity. Interferometry with larger masses, if macroscopic objects can be superimposed and still obey. Curvature, we will see interference patterns that classical theory does not support. The noise of spacetime, if spacetime is discrete. Ultrasensitive detectors should pick up a universal background noise, statistically the same in different places. Shadow of black holes, if information doesn't die, small corrections in the light near the horizon should betray quantum accounting. Halley would also cultivate the skepticism that made him great. He would ask if we are not confusing the map with the territory. Perhaps neither theory is wrong, just incomplete outside their habitat. Like ice, water, and vapor, the same substance. 3 phases with different effective laws. Relativity would be the law of continuous phase. Quantum mechanics, of granular phase. What we seek is the recipe that contains both. He would organize the chaos into 3 simple messages. Where the law is clear, there is direction. Anomalies are arrows, not obstacles in the way. Predict before explaining. Write down numbers that might fail in writing. Keep the hypothesis alive. New matter, new geometry. Let the heavens decide. Relativity versus quantum mechanics is not a duel to win. It's an interval between languages. When Halley saw patterns behind the apparent whims of comets, he didn't tame the sky, he refined the question. Here, the refined question is, under what conditions does geometry become probability, and probability become geometry? Until then, we call it mathematical chaos. Halley would call it a prologue, places where physics doesn't work. Edmond Halley. If Halley were alive today, he would do what he always did, draw an atlas, not of seas and comets, but of boundaries, places where our laws cease to be law and become tired hypotheses. He would mark with dark ink the points on the cosmic map where reality speaks another language. One interior of black hole's singularity, an event horizon on the outside. Relativity elegantly describes the curvature. At the event horizon, light loses its right to return on the inside. The calculations point to infinite density, a sign that our mathematics has broken down. Halley would write in the margin, law valid so far. He would look for observable clues near the horizon. Small discrepancies in the shadows of black holes. Subtle echoes in gravitational waves, any signature that tells how information survives or dies. to the first instant of time Planck scale before tilde 1043 yes. Space and time may not be what we think. Einstein's geometry demands a smooth surface. Quantum mechanics requires grain. At the encounter, foam emerges mathematical chaos. Halley wouldn't try to see this moment. He would try to hear it indirectly. Fossilized patterns in the microwave background. Statistics of primordial gravitational waves. The method, comparing long catalogs, as he did with the fixed stars in 1718. 3 extreme cores, neutron stars, and beyond inside. The pressure crushes atoms until only degenerate matter remains, perhaps exotic layers hyperons. Free quarks are equations of state clash. Halley would mark neutron-star collisions as beacons. From each merger, measure the deformability, the brightness, the gravitational wave, and adjust the law to the data, not the data to the law. For vacuum that is not empty energy from nothing, we call a field teeming with fluctuations nothing. If the vacuum is metastatic, a bubble of a lower state could rewrite the rules at the speed of light. Halley, who wagered on the return of a comet, would make new bets. If the energy of the vacuum changes with time, the growth of cosmic structures deviates from this trait. If it doesn't deviate, my hypothesis is wrong. 5 spacetime phase boundaries like ice, water, and vapor. The tissue itself can have phases. In certain regimes, collective properties emerge that do not appear in the parts. Superconductors and superfluids are general rehearsals. The classical fails. The quantum rules the macro. Halley would tick laboratories on the map, interferometry with larger masses, optical clocks in strong fields searching for minute effects that reveal the phase of the stage. 6. Gravity tensioners, dark matter, and alternatives. Rotation curves, exaggerated lenses, clusters too heavy for the light we see. Either invisible matter exists, or the law of gravity changes its accent on large scales. Halley would doubt himself in writing and let the heavens decide. Side-by-side predictions. Blind testing with new data. 7. Where cause and effect falter time arrow. Entropy gives direction to the film until extreme conditions cause it to oscillate. We won't see glasses shattering, but we might see statistics going off track. Halley would look for long series of measurements, subtle, persistent deviations, patterns in the noise. In the footnote of his atlas, Halley would repeat the credo that made him great, name the anomaly, collect long catalogs, bet on predictions that might fail, redraw the map when the edge moves. Places where physics doesn't work aren't holes in reality, they're invitations. There, the prevailing law says I don't know, and that is the phrase that opens the next page of the book of the cosmos. Call Halley back, not to follow a comet, but to track a trend, the void pushing to hard. If dark energy has a ghostly mood, the so-called less than 1 FW less than 1, the expansion not only accelerates, it shoots up. Space stretches so fast that no force can keep up. The result is not a boom, it's a hierarchical tier. The script of the tier first, the cosmic web unravels. Clusters lose their gravitational glue. Then, the galaxies break apart in on themselves, spiral coats of arms unravel. Next, star systems become unanchored, stars drop their planets. Closer to the end, cosmic tides overcome planetary bonds and molecules. Moments before, electrons are unable to keep up with the stretching of space. Atoms break apart. In its final breath, even the core gives way. The universe ceases to be structure. It becomes pure tendency. Halley would look at this as he looked at the comet of 1682. Lengthy catalogs, stubborn patterns, written bets. The comet was predicted to return in 1758. Here, the return is the curve of expansion. If the big rip is destiny, the signals are accumulating, now discrete, but consistent. What Halley would measure and bet on. Cosmic clocks level E as supernovae, if less than 1. If W less than 1 persists, the apparent brightness at large distances will become even weaker than at A equals 1 W equals 1. Baryon acoustic oscillations bow. The standard ruler will appear more stretched over time. The rate of Hz rises beyond what is expected by L constante. Structure growth weak lensing. F. Galaxies will form less structure than gravity would require. Growth becomes suppressed. Integrated Sachs-Wolf effect. The extra push from the vacuum will leave a larger signature. On the large scales of the microwave background, standard sirens gravitational waves, redistance measured. Bicompact binaries in greater than 1 z greater than 1 will detach from the scenario. Equals 1. Redshift drift Sandage Lobe. Test. When comparing the spectrum of the same galaxy over decades, the z-shift should indicate a more aggressive acceleration. He would write the predictions as he wrote about the comet's return, dated and falsifiable. If the data doesn't follow suit, the tear falls. If it does, the void is tuning the violin. How does one live in a world that tears apart? Halley would calmly reply, in order of effect. Long before atoms give way, technologies based on precision gravity GPS, stellar navigation, lenses begin to disagree with the static theory of dark energy. Then, mass maps show weakness in the growth of structures, as if the cosmos were tiring of putting things together. Only much later does the cinematic part come. Discipline skepticism. The Halley method. What if it isn't less than 1? W less than 1, but systematic in the data. What if it's modified gravity, not exotic energy? Yes, W varies with time, and today it only seems less than 1. Halley would keep the hypothesis alive, request independent measurements, and let the heavens decide. In the end, the Big Rip isn't an explosion, it's a contractive cohesion broken in stages. The universe doesn't disappear, it unravels, and Halley's lesson remains when reality creaks. You don't run from the noise, you follow the noise, with catalogs, with courage, with bets that might fail. That's how a comet got a man's name. That might be how we decipher if the void is pulling too hard. Big crunch collapso reverso. Edmond Halley. Call Halley back to the edge of the pier, not to watch the sky flee, but to imagine the sky returning. If the universe that is expanding today one day slows down, stops, and reverses, we will have the big crunch, a cosmos that breathes out and then pulls the air back in until its last breath. How can the collapse begin? Halley would look at the universe's energy budget like someone checking a ship's accounts. Before voyage, 3 paths would make the compass turn: curvature and density above the critical point. Enough matter visible plus dark for gravity to overcome expansion over time. Dark energy that changes mood. The push from the void weakens or even becomes attractive lambda less than 0, or a field that rolls towards a negative potential. Modified gravity. The law changes its focus on large scales, and expansion loses momentum. The script of the collapse in slow motion turning point, expansion, SLOWS down, comes to 0, and the scale factor begins to decrease. Islands reunite, galaxies and clusters are once again drawing closer. Collisions become the rule, not the exception. Heating of the underside. The CMB, cold today, warms up as everything compresses. The night sky takes on an oven-like glow. Final bursts of activity. Waves of star formation reignite with compressed gas. Black holes coalesce in a cascade. End tides when the shortening becomes fierce. Smaller structures, star systems, planets capitulate. Destination, classical singularity, or a quantum bounce, if new physics prevents infinity. How would Halley test the hypothesis written bets? He wouldn't preach the apocalypse. He would preach predictions. Notes in the style of 1758. Dated and forgivable. Deceleration parameter. If we head to crunch, Q should become positive in future eras. We will see a measurable transition in deep surveys. Redshift derivative Sandage Lobe, measuring the same spectrum for decades. The Z should drift downwards at certain intervals, a general break signal. BAO and HZ ruler, the apparent acoustic ruler, and the expansion rate will diverge from the scenario. Equals 1 W equals 1, pointing against the acceleration. Structural growth F. Instead of suppressing, structural growth will be less restrained. Gravitational potentials will evolve with altered sign ISW. Standard sirens gravitational waves, luminous distances measured by compact binaries, will shorten relative to the CDM in a consistent pattern and with the Halley method in 3 lines. Collect long catalogs, supernovas, bows, faint lenses, cosmic chronometers. Compare eras, as he did in 1718 with the fixed stars, to see if the cosmic fixed moves. Keep the hypothesis alive. Less push from the void or more pull from gravity. Let the heavens decide. What would it be like to live in a universe that keeps repeating itself? At first, nothing cinematic. small differences in distance maps, a slight change in the statistics of the structures. Much later in time, the background thermometer rises, the night sky brightens, the galaxies cluster together, the cosmic clocks advance. It's not an explosive ending. It's a continuous, moving curtain closing. Disciplined skepticism, Halley would ask. What if it's just bias in the data? What if we're measuring with the flashlight pointed in the wrong place? He would demand independent methods and prediction that can fail without excuse. Ultimately, the big crunch is the possibility that the universe is not an epilogue, but a cycle. Halley would endorse what he always taught: when the law creaks, it's not the end of science, it's the beginning of the next language. And he would write it, line by line, with the patience of someone who has already made a comet return on paper. Before returning in the sky, big freeze, eternal freeze. Edmond Halley call Halley to observe not a bang, but a cooling. If dark energy behaves like a constant W approximately equals 1, the universe neither tears apart nor returns. It stretches forever, diluting matter, light, and heat until almost nothing remains but thermal silence. The freeze frame script in extreme slow motion, loosening of the web. Expansion accelerates. But what is already gravitationally bound galaxies? Clusters remains together, isolated in islands. Fuel depletion. The rate of star formation falls. Cold gas becomes a relic. The last stars are born small and live long, faint trillions of years. Stellar twilight. Supergiants disappear. What remains are brown dwarfs, cooling white dwarfs, neutron stars, and black holes. A night of relics. Without new fuel, interstellar chemistry slumbers. Extremely rare stellar collisions punctuate the darkness. The era of black holes. They dominate the stock of gravitational energy and, in the end, evaporate through Hawking radiation on absurd scales. Heat death. The universe tends towards a state of maximum entropy. Energy is scattered. Temperature differences are non-existent. Work is impossible. How would Halley test written bets? Halley wouldn't sell destiny. He would sell predictions. QZ and HZ. If freezing is the way, QZ will tend to 1. Curves in deep surveys will converge to the de Sitter regime. Growth of structures F. We will see persistent suppression of growth on large scales, even with the same matter. A sign of the constant push. Cosmic star formation rate. The peak is already in the pass. The tail descends. Without recovery in multi-Z samples. Standard sirens, gravitational waves, luminous distances of compact binaries will follow the geometry of W approximately equals 1. Sustained systematic deviations refute the scenario. Redshift drift Sandage lobe. When comparing the same spectrum over decades, the Z-shift will indicate acceleration consistent with constant. He would write the date, margin, and error, as he did with the comet, and let the sky confirm or deny it. What is it like to live in a universe that freezes? In the short human term, nothing spectacular, slightly different distance maps, quieter neighboring galaxies, a night sky less fertile in births. In cosmic terms, the darkness grows, stars die out, the last lamps cool down, background radiation stretches to irrelevance. There is no final explosion, there is thermodynamic abandonment. Disciplined skepticism, the Halley method. What if W is not exactly -1, but varies slowly? What if gravity changes its accent on the larger scales? What if there is a future phase transition in a vacuum? Halley would keep competing hypotheses side by side and demand independent measurements. In the end, the big freeze isn't a tragedy, it's a trend. The universe doesn't fall, it weakens. And Halley's lesson remains intact. When reality whispers, collect decades, compare catalogs, bet on predictions. If destiny is cold, it will be the sky itself patiently that will sign off on it. Gravitational anomalies. Edmond Halley. If Halley were here, he would trade the sextant for maps of light curvature. He would follow what gravity does when it should behave and doesn't. He would call an anomaly not what is impossible, but what stubbornly refuses to fit into the calculations, where gravity seems too strong. Exaggerated gravitational lensing. Galaxies and clusters bend light more than visible mass allows. Either an invisible skeleton exists dark matter, or the law we use changes its focus on large scales. Galactic rotation curves. Stars on the periphery spin too fast not to fly away. For our book, We're short on kilograms. For the universe, perhaps we're short on laws. Where gravity seems like something else, growth of structures, the cosmic web sometimes grows less than gravity demands. Is this a push from the void, dark energy, or a sign of altered gravity? Cosmological tensions. The universe's rulers and clocks, supernovae, BAOs, CMBS. Standard sirens don't always tell the same story. It's not a mistake, it's a map of friction between scales. Lessons from mistakes that became science. Halley loved anomalies that teach us. Mercury's strange perihelion became general relativity. The drift of the fixed stars showed that the sky moves. Even anomalies that disappear with better modeling, like the acceleration of the Pioneer probe asymmetric heat or the oddities in flybys, have value. They force us to measure better. For Halley, every anomaly is an arrow on the edge of the map. Keep going this way. The Halley method applied to anomalies. Collect extensive catalogs, overlay weak lens maps, galaxy counts, X-ray clusters, cosmic background spectra. Where the sets agree or disagree, there's a clue. Compare eras. What is a small deviation today may become a trend tomorrow. Halley discovered the proper motion of the stars this way. By comparing centuries, bet on falsifiable predictions. Write down numbers that are likely to be wrong in writing. The bets that Halley would leave on paper: strong lenses, time delay. If visible mass is lacking, the delays between multiple images will tell us how much. If, even with dark matter, the numbers don't add up, suspect new gravity. Weak lensing plus clustering mass bias. Shear maps should match masses inferred by X-ray. Persistent discrepancies require more than adjustments. Growth F versus expansion HZ. If expansion accelerates, growth slows. Any pattern that breaks this antique relation is a signal. Clocks near gravity wells. Atomic clocks at different altitudes should disagree exactly as relativity predicts. Systematic and replicable discrepancies raise a red flag. Binary pulsars and gravitational waves. Energy lost by waves should follow Einstein's formula. Continuous and clean drift points to corrections. Standard sirens. The luminous distances measured by gravitational waves need to match the optical ones. A stable disagreement is not statistics, it's a message. Discipline skepticism. Halley would first ask, is it systematic? Only then, is it new physics? He would keep rival hypotheses side by side: dark matter versus modified gravity, and let heaven decide, without attachment. Why does this matter in your video? An anomaly isn't a plot flaw, it's an act change. It's where the scientific narrative shifts tone. By showing that gravity sometimes exaggerates, fails, or speaks dialect, you take the audience to the exact point where physics grows. Punchline. Halley style: name the anomaly, measure it until you're exhausted. Write a prediction that might fail. If the heavens agree, you haven't hunted down a bug, you've discovered the next law. Ghost galaxies. Edmond Halley. If Halley were alive today, he would trade his telescope for wide-field cameras and endless spreadsheets. He would hunt for ghost galaxies, enormous structures with extremely low surface brightness, so faint they almost disappear in the noise, but with gravitational clues that scream out. Some seem to fail to have stars for the mass they suggest. Others, on the contrary, seem to have too many stars for the gravity we measure. In any case, the map is uneven, and that's where Halley would come in. What are ghosts? Islands of inflated stars, diffuse, with a few bright points scattered across entire galactic areas. From a distance, they appear as fog. Up close, the enigma. How do they hold themselves together? There's a lack of visible mass for such an expansor. In rare cases, a lack of dark matter to explain the dance of the stars. Both options challenge the law. How would Halley track them down? The method is the same one that revealed the proper motion of the fixed stars in 1718. Lengthy catalogs and methodical comparisons. Stack deep images to extract the brightness profile. Counting and dating globular clusters. Excellent mass trackers to measure velocity dispersions of stars and planets in nebulae. To map neutral hydrogen high when present, look for weak gravitational lenses. The slight distortion of the background light reveals the total mass. Check the environment. Are they near giants that may have been stripped bare by tides? 3 hypotheses on the table. Failed giants, enormous halos that barely formed stars, lots of potential, little light, bloated dwarfs, small galaxies that have swelled due to supernova explosions, tidal forces, or feedback, scattering the stars, tidal ghosts, debris from violent interactions, with a diffuse glow that mimics stable galaxies. Bets that Halley would leave in writing: richness of globular cells versus mass. If they are failed giants, they will have many globular cells for the light they emit. If they are inflated dwarfs, the number of globular cells will be modest. Dispersion versus effective radius. In ghosts sustained by dark matter, velocity dispersion increases with radius. If dark matter is lacking, the curve becomes low and flat. Tidal signature, tidals, twisted isophotes, and asymmetrical velocity gradients suggest a tear-off origin. Metallicity, luminosity. If the history of star formation was poor, we will see metals that are low for their size, a break from the standard relationship. Weak lens stacking. A stack of dozens of ghosts should produce a shear signal, consistent with massive halos. Systematic absence of the signal favors the no halo scenario. Disciplined skepticism. Halley brand before proclaiming a new physics. Halley would ask: distance. Are we measuring too far away, inflating sizes, or too close? Underestimating mass. Contamination. Do foreground and background stars pollute the brightness? Selection. Are we only seeing the most dramatic ones because they ray the only ones that appear in our filters? Why do they matter? Ghost galaxies test the pillars of our understanding of galaxies: dark matter and gravity. If enormous halos exist with almost no stars, we learn about inefficient star formation and extreme feedback. If, on the contrary, some galaxies truly exist without dark matter, then either gravity changes its focus in certain regimes, or tidal processes manage to tear away halos. Both bold possibilities. Visual script for your video. Start with nothing on the screen and gradually reveal the diffuse glow after stacking frames. Overlay arrows showing the isophote twist and possible tidal tails. Show a simple plot: scatter versus radius with two curves, with halo and without halo. Close with the globular cluster counter as a ghost count. Punchline Halley style. Name the stranger. Tell everything you can. Write down the prediction that might fail. If the heavens agree, the phantom galaxy ceases to be a wonder, it becomes a new law, or an update of the old one. Rule-breaking particles in the laboratory. Edmond Halley. If Edmond Halley were alive, he would trade the London docks for the cold corridors of a laboratory. Instead of comet tails, he would follow statistical tails, stubborn deviations, small discrepancies that, added up over years, become a map where common sense sees noise. Halley sees clues and writes down his bets. What does breaking the rules mean here? It's not magic. It's two types of messages. Persistent deviation. A quantity always measures slightly outside the expected range and survives further testing. Forbidden process. An event that should never happen within the standard model. If it does occur, there is new physics. How Halley would proceed. The method. Long catalogs. Round after round of dice. Disciplined skepticism. First systematic, then miraculous. Falsifiable predictions. Tickets to the future with numbers and margins. 1 Giro du muon G to the muon is the electron's heavy cousin. Its magnetic spin reveals everything the vacuum hides. If the measured value stubbornly exceeds the theoretical estimate, it's as if unseen particles were blowing on the muon's compass. Halley's bet. If it's new physics, we'll see correlated patterns in other observables: rare decays, collisions that suggest light, heavy mediators. If the basic theory is that it's short-sighted hadronic inputs, for example, independent calculations and new measurements will shrink the voltage. 2. Non-universality among leptons and certain B meson decays. Quarks should treat electrons and muons as equals. If rate ratios deviate from the expected one, the balance tips. There may be new currents, extra bosons, leptoquarks weighing on the muon side. Halley's bet. The same deviation should reappear in sister channels. Same process, different ending. Angular observables and asymmetries will converge to a common pattern, and direct searches should sniff out the mediators, or the effect disappears with more statistics. 3 extra neutrinos, the sterile ones. Some experiments reveal short oscillation tracks that don't fit into the standard trio E, nu mu, nu tau. A 4th neutrino, Sterile wouldn't sense the weak force, but it would mess up the counts. Halley's bet, Halley's bet, Halley's bet. Appearances and disappearances must fit within the same set of parameters. Reactors, radioactive sources, and accelerator beams must tell the same story. If you don't get married, the ghost effect is systematic. If you do get married, we open a new family on the map. For neutrinalis double beta decay, this process is forbidden in the standard model. If it occurs, it shows that the neutrino is Majorana itself and its antiparticle, and that the lepton number is not conserved. Halley's bet, a characteristic energy line should emerge across different isotopes. Rates and dependencies match with a single effective mass without reproducibility. We return to skepticism. 5-electron, neutron electric dipole moment EDM. The standard model predicts minuscule ED-MES. Measuring any larger value reveals a new CP violation, a coveted ingredient. To explain why there is more matter than antimatter. Halley's bet, signals in different systems, molecules, atoms, free neutrons should correlate. Other CP observables will also react in the same energy sector. 6 light bosons, dark photons, and axions, if they exist, they mix slightly with the photon or with gluons, leaving fine traces, narrow lines and cavities, subtle polarization rotation, discrete excesses in beams and reactors. Halley's bet, consistent signals across different techniques, haloscopes, helioscopes, beams, colliders, and a clear relationship between frequency, mass, and coupling. Without this coherence, it's just instrumental noise. 7 rare symmetry breaking, nearly impossible processes, forbidden decays. Minute violations of principles act as a silent alarm. A single clean event can be worth a decade. Halley's bet, did you see it here? You'll see it there. The same signature must appear in independent experiments with different systems. The notes that Halley would leave on the laboratory door. If G2 remains high, channels X and Y rise together to that level. If they don't rise, correct the theory. If a sterile neutrino exists, this baseline and energy arrangement produces a trough, peak in probability. If it doesn't, it's archived. If there is decay without neutrinos, the same effective mass explains multiple isotopes. Otherwise, it's an artifact. If the EDM electrical discharge station ignites here, it should ignite there on a planned scale. If not, systematically. Skepticism that doesn't dampen curiosity. Halley would begin by asking, is it systematic? Is it selection bias? Is it an incomplete theory? Only then is it new physics. And he would keep competing hypotheses alive until the very last graph. Why this is gold for your narrative. Rule-breaking particles are not plot devices. They are the point where science grows. Each well-handled anomaly becomes a bridge. It either improves the theory we have or points to the one to come. Punchline Halley style. Name the anomaly. Tell the whole story for a long time. Write down the prediction that might fail. If the lab signs off on it, you haven't caught a mistake, you've just opened the next law. The greatest flaw in the universe may be our arrogance. Edmond Halley, our greatest failing may not lie in the cosmos, it lies in the pride with which we believe we already understand it. We call laws what works where our instruments reach, and sometimes we confuse map with territory. The universe owes us no lessons. Edmond Halley learned this through experience. He didn't treat comets as omens. He treated them as patterns. He wagered in writing that they would return and accepted that he could be wrong in broad daylight. When he compared catalogs and saw that the fixed stars were moving, he didn't defend his old idea. He changed his mind based on the data. Halley didn't worship certainties. He loved predictions that could fail. Scientific arrogance is wanting reality to bend to our language. Scientific humility is changing language when reality demands it. Today, faced with black holes that blend geometry and probability, dark matter that weighs without shining, a void that pushes everything away, the arrogant impulse is to declare, we already know enough. Halley's method whispers something else. Measure more. Compare eras. WRITE bets. Arrogance manifests itself in small things, calling an anomaly noise before understanding it, adjusting the graph until the line looks nice, preferring the model to the measurement. Halley would do the opposite. He would ask, what if this deviation is the entry point to a greater law? And without drama, He would put forward to competing hypotheses new matter or new gravity and let heaven decide. There's also philosophical arrogance, demanding that the universe be intuitive. We want cause and effect aligned, space smooth, time obedient. But the cosmos can be coherent without being comfortable. The role of science is not to simplify reality, but to illuminate complexity enough to act within it and to accept that the lighthouse always leaves shadows. Halley gives us a protocol against arrogance. Name the stranger, collect long catalogs, predict before you explain. Let the data kill your attachment. If the universe's greatest flaws are arrogance, the antidote is a rare blend of courage and humility. Courage to bet on numbers that might be wrong, humility to celebrate the mistake that points in the right direction. That's how one man lent his name to a comet, not by dominating the sky, but by listening when the sky disagreed. In the end, maybe the universe isn't failing us. Maybe we're learning to ask better questions. And that, in itself, is a revolution. If the universe is falling apart, you saw the signs first. Edmond Halley, if the universe is falling apart, it doesn't start with a bang. It starts with signs weak, stubborn, almost shameful to exist. An atomic clock that disagrees with itself by a thread. A diffuse galaxy that weighs too much for the light it contains. A lens map that warps slightly beyond what was predicted. Almost nothing, almost everything. Halley would have recognized that scent of the future when he compared catalogs and discovered that the fixed stars moved. The sky didn't shout, it whispered. He placed his bet and waited. The comet returned. Reality confirmed it. That's what you're doing now, listening to what the cosmos doesn't yet know how to say aloud. If the universe is falling apart, you saw the signs first because you learned to look where others blink. You saw the missing glow. In ghost galaxies, the expansion accelerating a little too much. The statistics that deviate by centimeters on the graph. It's not superstition, it's an emerging pattern. It's the ancient law crying out for help. Halley would leave a note at the bottom of this video. Name the stranger. Compare eras. Bet on numbers. If the sky denies it, learn. If the sky confirms it, publish it. You've already done the hardest part, you noticed. Curiosity is the first tool, method, the second. Together, they become a beacon. Because when reality creaks, arrogance demands silence, but science demands listening. You are not seeing the end, you are seeing a shift in language. If the energy of the void tightens too much, if gravity changes its accent, if time hesitates, so be it. The observer's role is not to save the rule, it is to discover the next one. So remember this phrase like you remember historical events in an almanac. If the universe is falling apart, you saw the signs first.